So thank you everyone for coming. And my name is Boris Larin. I'm a security researcher at Kaspersky. And at work, I'm doing reverse engineering. Usually, I'm analyzing exploits that we find every day, and my main focus is to find the 0 days exploited in the wild. And lately, I found a few of them. So all of them were in active use by cybercriminals and national state actors. And today, I want to talk about another thing that I really care about. It's video game console hacking. So today, I'm going to talk about how I hacked Blu-ray drives of PlayStation 3 and PlayStation 4. And well, if you're asking yourself, like, why I decided to do this kind of research? Well, I was looking into PlayStation stuff for many years. Like, I know a lot about that. And I personally, I was always wondering about like how Blu-ray disc drive, how it works, how discs are verified. And because, the security of Blu-ray disc drive, it's a really essential part of security of PlayStation because games, they are distributed at optical media. So that's why drive should contain the best security possible. But at the same time, it also makes it a very interesting subject for security research. And I already presented this research at CCC in Leipzig a few months ago, but today it's OffensiveCon, so I want to talk a little bit more about my firmware reverse engineering methodology and actual exploitation. And before I continue, I need to give the following disclaimer. So first of all, this research, it does have nothing to do with my employer, and this research is done purely of curiosity and presented for educational purposes. And well, this research, it doesn't anyhow help, support, enable, or endorse to breach the copyright law. I will be talking about security vulnerabilities and how I got code execution on the thing, but my findings, they do not lead to full compromise of security, and it's not possible to use my findings to circumvent copy protection, and that's the reason why I'm even talking about that. So probably all of you are familiar with what Blu-ray disc is. Well, Sony, they did extremely well with PlayStation 2. In case if you don't remember, it was the very first game console that supported DVD discs, and people were buying it just to watch DVD movies. And Sony, they wanted to repeat their success with the next game console, PlayStation 3. And it's really easy to discern that just by looking at the timeline of events. Like specifications were finalized, and the first commercial Blu-ray disc drives, they were released just a month prior to PlayStation 3. And Sony, they succeeded. Right now, even Xbox uses Blu-ray discs. And actually, physical format of Blu-ray discs, it's very well documented in white papers and patents. These documents, they reveal what types of discs exist and what areas are present on discs and how these areas are different from each other, what structures are stored there. So if you are really interested in this subject, I recommend you to read these documents. But these documents, they don't reveal one simple thing, how regular Blu-ray discs are different from PlayStation discs and how PlayStation discs are verified. And well, I was always curious about that, and I was thinking that maybe drive firmware may reveal some details. So let's talk about PlayStation Blu-ray disc drives. And there have been a lot of different hardware revisions. If you will unpack PlayStation 3 firmware update, which is encrypted, you will find that encrypted firmwares for 12 different drive models, which is a really huge number, I believe. And here you can see the PCB of the first ever Blu-ray disc drive for PlayStation 3. Design is quite complicated, but my microcontroller, it's produced by Sony. And after some time, Sony, they've decided to switch to microcontroller of another company, Renesas. And well, I don't know what they were thinking, but after that, they were switching between Sony microcontroller and Renesas microcontroller for each new hardware revision, like Sony Renesas, Sony Renesas. Well, maybe they just wanted to diversify this platform to make hacking much more harder. And well, they've been much more consistent with the Blu-ray disc drives for PlayStation 4. All of them, up until recently, were based on Renesas. And if you will unpack PlayStation 4 firmware update, you will find the firmwares for 6 different drive models. And there also was a new addition to the family. Just recently came up new revisions with MediaTek microcontroller. So Renesas is the most common microcontroller for PS3, PS4, and that's why it's my subject of this talk. So how did we get the not encrypted firmware in the first place? And actually, this technique, it came out from Xbox 360. So here you can see a picture of a very famous kamikaze hack for Xbox 360 drive. It was developed by quite talented researcher Jeremiah. So this hack, it abused the fact that quite often firmware is stored on a flash chip that is a separate die inside the package. Well, this way it's much more easier for manufacturers to produce such chips. But this fact, it also makes it somehow easy to get access to firmware if you are able to decapsulate package. And in this hack, like what Jeremy did, he was able to disconnect one of connectors from flash die to mine die, and it led to removing write protection from this chip, and it made it possible to just flash your own firmwares. But if you are able to decapsulate, you are also able to get firmware from it. And here you can see decapsulated package of Renesas microcontroller for PlayStation 3 Blu-ray drive. So this slide, it demonstrates steps that you need to accomplish to get firmware from internal flash. So first, you need to use exit to decapsulate microcontroller. And when I say you need to use exit, I mean never try to do that at home because it's really dangerous. And when you do that, if you do everything right, then this microcontroller, it still will be in a perfect working condition. And then you can use a special tool, it's called Logic Analyzer, and then you can use it to sniff data bus and understand how you can, what commands you need to use to read the whole flash contents. So then you just cut these bound wires and rebound them to your own printed circuit board and like read the flash contents with your own external tools. So these steps, they actually were done not by me, they were done by another researcher who had much more experience with this kind of stuff. But, well, he shared his dumps with me and with other researchers from our community. And the flash on the internal flash, I mean, the firmware on the internal flash, it was not encrypted because, like, Sony, they didn't consider it as a security boundary. Like, who would look into internal flash, right? And like to start reverse engineering, I only was needed to find out like what architecture it's compiled for. And I did some research, well, with Google, and I found out that Renesas, they got a number of semiconductor businesses of huge manufacturers such as Hitachi, Mitsubishi, NEC, and well, they got a really huge list of microcontrollers. So everything is present on the website. And also there were some documents, and they revealed that their Blu-ray chips are also based on H8S architecture. And quite luckily, this architecture, it was supported by IDA Pro back then, so it was very easy to just jump in and start reverse engineering work. Like the only problem that I've encountered is that jump tables were not recognized properly, but it was still very easy to fix with scripts. And here's a few notes about this architecture. It's really nice RISC-like architecture. It reminds me x86 a little. Quite easy to work with. Here's a small snippet of assembly. And well, you can get 3 different compilers for this architecture. For me, it's quite fun that each of them uses different calling convention, and there are even differences in calling convention between different versions of Hue, which is the official compiler of Renesas for this architecture. So I began reverse engineering work, and well, it was quite tricky because, like firmware, it was really large in size, like 2 megabytes, and there have been no strings at all. And well, in case you are wondering how the developers were able to debug the firmware without debug messages, well, actually, a special log trace functionality exists in this firmware, but it takes only ID of a string instead of string, and then this ID is converted to string inside special software the developer has. Probably it was done due to size constraints because like firmware already occupies like the most of space that is available here. So well, developers, it's a common technique. They usually do that this way, but it's bad for reverse engineering for sure. And yeah, I began reverse engineering, and like the first thing that you want to do when you analyze some new firmware is that you go to the website of the manufacturer. And if it's possible, you might want to get source codes, you need libraries and compilers, and you need all of that to make the process of reverse engineering much more easier. Like you can compile these sources, and in with your firmware, you might want to generate fluid signatures. and use it with IDA Pro. And you also is very interested in getting definitions of hardware addresses and structures. And well, Rinsas, they provide a really huge stuff for download, so respect for them. And well, unfortunately, any DVD Blu-ray related stuff, it was not available publicly, and it's really complicated the whole project. Like everything that you're going to see, I come up with it with the help of reverse engineering. And also, Rinsas, they own a really huge list of real-time operation systems, and some of them are available for download. But yeah, and also official compiler is available. So it also is very useful, as you will see. So, well, I've got this compiler, and I was looking through the files of it to find any sources or libraries, but there was not any, because it appeared that all of them are stored inside packages, and only necessary files are unpacked during compilation to temporary folder. So what I did, I just found where this algorithm is located, and wrote my own utility to unpack all files. And I was not able to find any useful information about hardware there, but it was possible to generate IDA Pro fluid signatures. And many of such functions, they were used by PlayStation firmware, so it was a really useful finding, I believe. And the next step that I would usually do when I'm analyzing some firmware is that I try to find functions of real-time operation system. It is a very important step because control flow and data, it might be passed between different tasks that are running at the same time, and you really need to follow that during your reverse engineering work. And like, as I previously said, I got a lot of real-time operation systems from Renaissance, and all of them were kind of similar, but still had some differences, and in most cases, they were written in pure assembly for different architectures. And nothing really closely matched real-time operation system that was used in PlayStation firmware. So in the end, it was not really useful. But here is a great life hack that I would like to share with you. Like, the best thing about reverse engineering firmware developed by a Japanese company is that it most likely will have a real-time operation system that follows a micro-industrial Tron specification. And this specification, it's really great. It defines names of functions, their arguments, and etc. There are more than 300 pages, and it always saves my time and my life. So I really recommend you to do that if you encounter some other case like that. And the next step that I would usually do is that I try to understand how I can communicate with my target, like, and what logic I'm able to interact with. And well, Blu-ray drive, it communicates through an 88 protocol, and here provide hierarchy of 88 protocols. So at the bottom, we have physical interfaces. We have ETA or PETA. Previously, it was known as EDE. It's obsolete version of this protocol. And then we have SETA, which is more modern version of this protocol. And on top of that, we have two distinct command sets. We have ATA command set. It's used for hard disk drives. And then we have a TAPI command set, which is basically just a transport for SSI commands, and it's used in all other cases. And well, each device, it may have different SSI command sets, because we have a primary command set, it's common for all devices. And then we have a device-specific command sets. And for Blu-ray disk drive, there are even two competing specifications. So primary command set, it implements inquiry command, and it provides some basic information about like your device, like name of the manufacturer, name of the device. It's basically what you see when you connect disk drives to your computer, right? And well, what you do when you reverse engineering some firmware for disk drives, you just look for such information, and you will find a handler for inquiry command, and then you will find a handler for all SSI commands, and then you're good to go from there with your reverse engineering work. So yeah, this is basically the roadmap that I'm usually try to follow, like get firmware, recognize CPU architecture, try to get information about this hardware, but it was not possible in this case. Then you identify standard library functions, identify functions of real-time operation system, and pinpoint interesting logic to find the vulnerabilities in it. So, well, the next step that would be also awesome to perform is to find a way to somehow emulate firmware, because it will, well, dynamically it will really aid us in static analysis. And also getting code execution will be awesome because it will help us understand hardware much more better. Because we will be able to interact with different registers to see what happens and how hardware really works. And GDB, it actually includes a simulator for this architecture. So you're just able to compile it, then you convert your firmware to a file, and you're actually good to go. You can emulate some snippets of code. But I actually, I'm really huge fan of IDE Pro, and I really like to use it as a GDB debugger GUI. But it has some flaws, of course. Like, well, recently it was improved a lot, but back then there was it was quite buggy. It supported only a few targets, and it's closed source. So at some point I decided to write my own GDB debugger plugin. And it was a very good decision because it saved a lot of time with this target and others officially not supported targets. So here's just a shot of how it looked like, just for reference. And while I was reverse engineering firmware of PlayStation, I actually was looking at multiple firmwares because it appeared that there exists Blu-ray disc drives for PC that also have this RINSAS microcontroller. And well, they were manufactured by Hitachi LG Data Storage. And of course, like how it often happens with PC peripherals, you can get not encrypted firmware from firmware update utility. And well, PC and PlayStation firmwares, they were different, but it was clear that they're built using the same SDK because many Blu-ray hardware-related functions were the same, and well, all devices, they were the same, and they were accessed by the same addresses. And also, PC firmware, it used the same cryptographic processor, but contained a little bit more debug strings, revealed the code name of this RINSAS platform for Blu-ray drives. It's called Indigo 3 internally. So on previous slide, I mentioned the cryptographic processor. And when I began reverse engineering this firmware, I found out that a really huge part of it is occupied by crypto-related functions. And these functions, they are used to communicate with a specially dedicated cryptographic processor. So, and it's really effective in protecting all the secrets. You're not able to just dump firmware and reverse engineer all of it. This component, it protects it. And like the logic of communication with this processor, it's really complicated. Here I provide a few graphs for some of such crypto-related functions. And for me, it was much more easier to understand the logic of LLVM obfuscated functions than understand logic of this communication. So here you can also see a small snippet of one of such functions. And it's clear that, well, there is a possibility to load additional modules and additional keys for this thing. And, well, actually, I don't know like why it was made so complicated. Maybe there was some size constraints on side of cryptographic processor. So this communication, it really was needed, and it was done in a way to try to like perform security by obscurity. But yeah, what I wanted to do, I just wanted to change some of these values that are set to registers, you know, like flip some bits and see what happens. And to do that, you actually need to get code execution. So right now, let's talk about exploitation. And well, last year I gave a presentation at ConseQuest titled Hacking Microcontroller Firmwares Through USB. So you can find more details by the following link if you're interested. So in this research, I examined how awesome is the protocol of control transfers is for USB exploitation. And well, I believe a CSI protocol might be even more awesome, but it's less common for sure. So how it works? Client, it sends a special common descriptor block to device. And CSI devices, they usually support a very large number of different commands. And these commands, they are used to transfer data from and into device. And the device, it also provides status of command and the error code. So, and also these commands, like the very common fields of these commands, they include some logical block address or size of transfer. And all of that, it makes this protocol very easy target for fuzzing. But you need to be aware that if you actually start to fuzz your target, you may find some bugs, and it may happen that your bugs will corrupt internal flash, and in that case, you will just get a bricky device, because if internal flash is corrupted, it will not boot, and like you don't have other options like to do besides buying a new one. So I found my vulnerabilities through static analysis. And while I was looking into this firmware, it really felt like it was developed by some third-party company, and then some parts were implemented by Sony engineers on top of it. Because all general SCSI commands, they were looking fine, but not commands implemented by Sony. Well, many of them didn't have boundary checks. Like, this is perfect example, I believe. Like, it has operation code E1, and this command is used to for identification of Blu-ray disk drive and the video game console. So the main purpose of it is to implement security. But of course, transfer length is not checked, so we have out-of-bound writes to some static buffer that is located by the following address. So let's talk about memory map. That's what I was able to come up with during my reverse engineering work. So at first, we have non-volatile memory. We have ROM with bootloader. We have flash with firmware. Then we have volatile memory. We have SRAM and DRAM, and also addresses of different peripheral devices. So first is SRAM. It's a static random access memory. It's very small in size. It's executable, but it's configurable. And it contains interrupt vector table, it contains code of real-time operation system, it contains important variables and pointers, and also stacks for tasks. And another one is DRAM, which is dynamic random access memory. It's very large in size, 8 megabytes, and initially I didn't know exact memory location because most of the time DRAM is accessed through DMA from firmware. And it's used to store information about disk, to store information from a CSI client, and it also stores, it's used to store information about information that do not fit to SRAM, because like SRAM, it's really small, and firmware is large. It needs a lot of space to store its variables, so why not to store them to DRAM? And actually, these two memory regions are used to do just that, to store variables of firmware. And I found that they exist. The second one is actually unused in PlayStation firmware, but I found out that it exists from PC firmware. So we are able to write some static buffer located in this region. So how can we exploit that? And well, exploitation turned out to be very difficult because all variables in this firmware, they're located at fixed static addresses. So it means that heap exploitation techniques, they are not possible. And at first, you need to find a very good exploitation primitive, and you need to write many variables upon reaching this primitive. And you need to do that without crashing the device. And I need to mention that like debugging is complicated. GTAG, of course, it's disabled. So like you have to like do debugging blindly, just like to see like if your device crashes then, and make some guesses what happened. And well, I ended up reverse engineering the whole firmware and like all functions that access data in this region. And there were, of course, no virtual function pointers, so there were no good candidates for write. And there have been a lot of structures, other variables, not much pointers, but eventually I found a good exploitation primitive. But while I was looking into that, I found a new oct0xor face, and it was a new source for vulnerabilities. So DSP registers, they're very interesting because they're responsible for most of the disk drive related functionality, like ATAP interface, lather, servo, disk data demodulation, DSP firmware loading, and etc. And it would be so awesome if we had access to it. And actually we do, like the whole area of DSP registers, it's available for read and write through special SCSI commands that are available for do just that. So here they are, it's just a read buffer command and SCSI write buffer command with special buffer IDs. And looks like it's a pretty standard diagnostic functionality because exactly the same functions, they also existed in PC firmware produced by Hitachi LG Data Storage. So do you remember when I said that DRAM is accessed mostly through DMA? Well, several registers available in this DSP region, They are responsible for the DMA, and firmware uses them to copy data from and into DRAM and map DRAM offsets to some memory addresses. So I did some reverse engineering, and I found out that those regions that are used by firmware to store variables, they are actually mapped using these registers from this P region. And it works like this. So this hardware, it has 4 groups of memory mapping registers, and 2 groups are set during initialization to specific values, and others 2, they set frequently but different functions to different values. So I decided to show them. So, and each group of these registers, they map specific amounts of data from some DRAM offset to predefined memory addresses. And here you're also able to see to which memory addresses, which DRAM offsets are mapped. And it's worked like this, calculation as follows. DRAM offset, well, the value that is set to region register, it's multiplied by 4,000, and then is added to either first half of DRAM or the second half, depending on the bit that is set. But that's not all. Like there is also specially dedicated registers that allows you to read and write any double word from and into any offset of DRAM. And here provide code for doing just that. And of course, you can reproduce the same logic with the multiple SCSI commands that I showed you before. So like we have access to DMA with SCSI commands. Are we able to manipulate contents of DRAM? And I see multiple ways how to achieve this. First, we're able to remap this memory 1 region to another DRAM offsets, and then use our out-of-bound writes exploit to write some data there. But it may lead to different behavior, and as already mentioned, debugging is quite complicated. And another option, we just able to use our DMA registers to write and read data directly. But in firmwares that I've got, actually it was not true, because these registers, they were in active use by firmware. So like if I just will try to write something there, most likely it would lead to a different behavior. But still, I was thinking that I may exploit that. So I needed to test my ideas on real hardware. And actually, there are 2 ways how you can do that. One option, you can jailbreak your console, install Linux, and just issue your SSI commands to Blu-ray. Another option, disconnect Blu-ray drive from your console, connect it to PC. And it's, of course, more convenient. And it was really easy to do because, you know, on AliExpress, you can buy very different things. Like there were tools that you can use just to connect your Blu-ray drive to your computer. So made order and got it. But it was done for, like, it was designed for PS3, but because, and I wanted to try it on PS4 drive, but like PS3 drive and PlayStation 4 drive, they were like very similar. Like the only difference was in connectors of OFC cable. So I just modified it with scissors and it worked perfectly. So yeah, that's the whole setup that I've got. And well, the first thing that I did was to dump this P region, and that's what I have seen. Like the value of DMI request and the address of DMI request. So these values, they were set to zeros. And it will indicate that, well, it will indicate just one of 2 things. It's either this functionality is not present at all in hardware revisions that I've got, or it's just unused. And it was quite surprised, but it was just unused. Because in some later firmwares, Sony decided to stop use these DMA registers to access DRAM, and they started to access it just through absolute memory addresses. So I've got full read-write access to DRAM. And right now, let's talk about how you can do cool stuff with full access to DRAM. Well, usually DRAM is full of this data that gets transferred to your console. But when there is no disk inside, it's unused. There are a lot of space, and it's used for drive firmware procedure. And this procedure is very well known. It's already documented. If you're interested, you can check our wiki. And it's exactly the same for PS3 and PS4 drives. Here I explain how it looks like from the point of view of drive. So at first, block of firmware update, it's received with firmware write buffer command. And firmware checks, is it a first block? If it's the case that it will initiate some special structure. And then it stores this block to DRAM and checks if all blocks are received. And the next step, when all blocks are received, it will try to validate the hash. And if hash is correct, it will start to decrypt firmware. But it may take some time. And well, how it was intended to work is that a console, it should send a test unit ready commands to check whether firmware was already decrypted. And when it's already decrypted, there was a special hack made that would copy firmware update to SRAM and execute it. So do you see a problem here? Well, basically, it's time of check and time of use vulnerability. Well, if we have access to DRAM, we're just able to send firmware, wait until it will be decrypted, and then we can use our DMA trick to read this decrypted firmware and also modify it. So initially, I had only these firmwares that I got from the friend who were able to get it from the encapsulated microcontroller. But with my hack, I got this one, and this one, this one. It's PS4, by the way, and this one. It's all of this. It's different hardware revisions of PlayStation Blu-ray disc drives. And on this stage, well, manipulation of DRAM to get code execution, it's really trivial. And you know, like usually when you exploit such devices with internal flash memory, you need to be really careful, because if you do something wrong, flash will be corrupted and you will get a bricked device. But in this case, in boot, special emergency boot firmware exists. So if you got something wrong, you still will be able to unbrick your device. But my exploit worked on first attempt. And so why did it happen? Most likely scenario was, well, when this firmware was handed from third-party contractor to Sony, they didn't really understood security risks that are represented by DSP registers. And this functionality exists for diagnostic purposes, it's for sure, but nobody considered the danger that it might represent. And well, code execution, finally it allowed me to make some experiments. And well, like the whole community, it always wondered, like, what is this secret data that Sony put on disks when they're processed at factory? Well, finally I was able to decrypt it, and there is nothing interesting inside. So yeah, just zeros and some few bits that set some flags. So yeah, it was not worth waiting for. But for me, it was interesting to take a look on how keys are obtained from disk, because it should be somehow related to the way how disks are verified. Well, for PS3, there are two kinds of disks, just two kinds of disk keys, and one of them is used for decryption of disk data, and another one for encryption of saves. And all of this is exactly the same for PS4. And well, I found out that these disk keys, they returned by crypto processor, but only after drive identification. And I was thinking that the logic to construct and read these keys, it should be in crypto processors then. And well, drive identification in crypto processor of optical disk drive is the main thing behind optical disk drive security. Because drive identification is secure and performed with per console keys, and I only know two ways how to get those keys. You either need to hack crypto processor of your console or hack crypto processor of Blu-ray disk drives. And of course, it's very hard to achieve such hacks, and security model it's very effective against widespread piracy. Because much more simple ways to part games, they always existed. Like, for example, if you hack firmware of PlayStation, like kernel, you easily can pirate games. But if you hack firmware of PlayStation Blu-ray drive with mime hack, you can't pirate games. And I was thinking like how to better illustrate this security model. And this is the best what I was able to come up with. So we have two floating islands. It's our firmwares, and they support white castles. It's crypto processors. And take notice that there are no entrances to these crypto processors. So like you are not allowed to get inside. But also a secure communication happens between console and Blu-ray drive. It's used to securely transfer these keys and share disk data. Like probably it looks like this. And well, you're not allowed to bypass this secure communication. But if you hack firmware of console, you easily can bypass it. Like you just get disk data, you modify kernel, and then you just run your games. But if you hack firmware of the Blu-ray drive, you're not able to put your own keys to hack to crypto processor without hacking crypto processor. So like hack for firmware crypto drive, it doesn't really make a difference. And well, I finally was also play around with the crypto processor. And well, what I did, I just loaded crypto firmware from PS3 drive for PS4 drive, and the PS4 drive started to behave exactly like it should for PS3, like even addresses of registers have changed. So it proved my theory that firmware really exists. And another thing that I wanted to try, initially, try to change some bits. And it also didn't work out because I found out that if you change any of such values, crypto processor just hangs, and after a few errors, it will just, well, it will stop responding at all. You have to reset the device. So it appeared that the logic of these complicated functions, it works like this. So at first, a special seed for the hash is provided. Then firmware provides commands and its arguments, and then provides a hash to verify previously set commands. And of course, all this information is also encrypted. And then hardware, it's a crypto processor, it executes. At first, it verifies all this information, and finally executes these commands. So I was playing around with it, I was trying glitching and such analysis, but eventually I lost my interest because, well, breaking code protection, it was never the goal. And well, while I was reverse engineering firmware a little bit more, I found out that crypto processor most likely it exists only for crypto stuff, and there is especially dedicated hardware functionality that exists for doing disk drive security. And I found out it with the help of the first ever Blu-ray drive. So you already have seen this on previous slides. It's a PCB for the first ever Blu-ray drive for PS3. And there are a lot of components, but here are the most important ones, like memory controller. It's produced by Sony based on ARM. And then we have a NOR flash chip, is the firmware. And well, you see 1 megabyte NOR flash with firmware. It means that firmware, it's actually executed from external flash. And the data, it should be decrypted on fly. And of course, if you dump this firmware from flash, you will see that encryption algorithm is based on XOR. But so we have a XOR stream of fixed size, it's quite large, but still what you usually want to do in such cases is what you always do. You just find some spaces that are filled by zeros, try to XOR two streams together, and you will get original key stream. And then you can use it to decrypt or encrypt very small pieces of firmware, very tiny pieces, but in our case, it was still enough. Well, because code, it's executed from external flash, but integrity of firmware is checked at boot. So you're not able to get your flash programmer to this thing and first read, modify, write it. No, it doesn't work because integrity, it will be checked at boot. But, well, we're able to observe all memory accesses from CPU to external flash with the logic analyzer. And of course, we are also able to modify these read accesses with FPGA. So we can write a small payload and encrypt it with a recovered store stream. And then we can modify memory accesses from CPU to get this payload executed. And then we can use it to read plain text and leak it. So in result, we have code execution and firmware done. And this firmware, it was quite interesting. It contained a little bit more debug strings. And also there was a really huge, well, there was a special serial monitor with a really huge list of commands. And well, it also had a cryptographic processor but it was much more simpler than the one that Renesas had. Like it basically just you just set ID of command and keys to some predefined offsets in crypto region and initiate operation. And well, it also had a firmware. It's loaded by boot ROM, and it's also quite funny that like engineers initially they intended like you should not have access to this crypto region because if you try to read it from Flash, you will get a garbage. But if you like, how you should do that? You should use special functions that are present in bootloader. But all of them, they had integral flow checks, so still like you just able to use them to read the whole crypto region. And of course, it will be also still bypassable with return programming. But it was still fun. Like you can get some strings that should not be available, like to get otherwise. And well, Sony microcontroller and Renesas microcontroller, well, they are completely different platforms, and it means that like all peripheral devices, they are different and should be accessed differently. But I found out about existence of one single peripheral device that is accessed exactly the same, and it will mean that Sony they moved this component from their older drives to Renesas drives, and yeah, it's just accessed differently. Like in Sony microcontrollers, it's located in some special memory region, and in Renesas, it's accessed through DSP registers. So I assume it's actually this specially dedicated disk security component, and it performs some interesting things like firmware. It calculates CRC of disk ID and XORs it with magic, and puts it in registers of this component. And well, if you try to modify it, then crypto processor it will not be able to get these keys. So I'm sure that it should be a part of the way how disk is verified. But to find out the rest of the algorithm, it will be a really huge problem because quite likely this logic is implemented in hardware, and reverse engineering hardware is exactly not like reverse engineering software. So. Well, here's time to make a conclusion for my talk. And well, I think that Sony and partners, they actually made an exceptional work because security model, it's really good and has proven itself. Because imagine PlayStation Redis drives, they existed since 2006, but no public hacks since then. And like there are many different parties who are commercially or not commercially interested in this kind of stuff, and nobody was able to do that. And also a lesson that can be learned, firmware, it's always is very easy to hack, but hardware is another case. So if you're actually interested in side channel analysis and glitching, I can recommend you to take a look at this real-world target, but I believe it's a very tough one. And I also want to give my respects to everyone who also ever looked into hacking PlayStation Redis drives. And right now also comes a time to talk about responsible disclosure. So initially, I already presented this at CCC, and just a month before my talk, a security team, they reached out to me and kindly asked to provide more information about these vulnerabilities. And of course, I provided them, because why not? Well, and it was quite a surprise, but just 1 week later, I got a message like, hi, so we decided to launch a new bug bounty today. Would you like to participate? And I mean, wow, of course. Like, I already sent you bugs. So yeah. And all vulnerabilities, they were patched, and I've got 1 high and 2 medium severity bugs. And all vulnerabilities were fixed in the latest system firmware version, which is 7.02. It's still the latest at this moment. So it seems that I have become a first ever researcher who has won PlayStation bug bounty. And yeah, I mean, Sony, like, my experience with them, like, I know I don't know about other researchers, but my experience was really awesome. Like, they were really fast and awesome. I mean, so I can recommend you to work with them. we're still waiting for them to announce this bug bounty. And well, I believe like it could be a very legit way to make money on your free BSD UAPs, because I guess demand for them is not that high. So yeah, if you're interested, slides are available by the following link. And thank you.